Hi y'all, welcome to Miss Clarke's chemistry class. This is the second lesson in a series of several lessons about gas laws. In this lesson here, we're going to talk just about Boyle's law. Boyle's law deals with pressure and volume. I'm going to have lessons on all of the laws, so make sure you subscribe so you don't miss a single one. Go grab your notes, grab something to write with, and the dreaded calculator. Y'all know math is my favorite. Let's get started. Kinetic molecular theory describes the why gas particles behave the way they do. Boyle's law is a law that describes what gases do. Boyle's law deals with pressure and volume. If we've got a container of gas, and let's say we've got some gas particles in there. So we have a container of gas. Now remember, part of the kinetic molecular theory says that gases have hardly any volume. There's mostly empty space. So let's say that I take all of this gas and I reduce the size of its container. We could still fit all of these gas particles in here. The only problem is, if we remember another portion of the kinetic molecular theory, it was that gas particles are in constant motion and they're making these collisions. And the more collisions they have, the more pressure they have. So in this first scenario here, these gas molecules, they're moving, they're bumping into things. These arrows are showing their path. They're all moving, but they have a big space to move in. So their pressure is whatever it is. But now we take all of these gas particles and we stuff them into a smaller container. So in situation 2, the volume decreased. There's still the same amount of gas particles, but they don't have as much room to bump around in. So their collisions are getting more frequent and more powerful. If the collisions increase, that means pressure increases. So when we talk about pressure and volume, if we decrease the volume, the pressure increased. Let's look at that a different way. Okay, so in this example, I have a little balloon in a syringe. I want it to be a closed system, so I have a lid here. And if I push the plunger in, I am decreasing the volume. So if I'm decreasing the volume, I should be increasing the pressure. Let's watch the balloon. As I'm decreasing the volume, the pressure is increasing in the chamber, which is pressing down on the balloon, so the balloon is getting smaller. If I release the plunger and let the volume increase, the pressure is going to decrease, allowing the balloon to go back to its original. Let's see what happens when I increase the volume. When I pull the plunger, if I'm increasing the volume, I'm decreasing the pressure, which is allowing the balloon to get bigger because there's not as much external pressure pressing on the balloon. Let's look at this again in a different syringe. So we've got a marshmallow. He's so happy. He's got a little happy face. Now let's watch him. I'm going to increase the volume, decreasing the pressure, which is causing the marshmallow to expand because it doesn't have as much pressure pressing on it. Now let me decrease the volume. And we can watch him shrivel up. As I'm decreasing the volume, I'm increasing that pressure. That pressure is pressing down on the marshmallow and he is getting smaller and smaller. I have this other smaller one. I don't know if you can see it as good as the bigger one, but it's here, so we might as well look at it. Now let's decrease the volume. So we're increasing the pressure, which is causing the marshmallow to shrivel up. Let's do that on this one more time. So I've got a really big volume. I'm going to decrease the volume, increase the pressure. And look how shriveled he becomes. Okay, so that's Boyle's law. Pressure, volume, inversely proportionate. If we were going to draw that on a graph and we had pressure and volume, as the pressure decreases, the volume is going to be allowed to increase. If we wanted to show this in a mathematical equation, we would say that the pressure and the volume of the initial situation is equal to the pressure and the volume of the second situation. If the pressure increases, then the volume is going to decrease. If we think about this in the opposite way, if we have our container of gas, they're having collisions. They're maintaining a certain amount of pressure. And then if we increase the volume of their container, and if we've got the same amount of gas particles, there's more space. Their collisions slow down. Their particles can slow down. So in this example, if our volume increased, it allowed greater space for our particles to spread out, which decreased the amount of collisions, which means we decreased the amount of pressure. Let's look at a math problem. At 1.20 atmospheres, a sample of gas takes up 3.14 liters. If the pressure on the gas is increased to 1600 torr, what will the new volume be? Couple of things. Let's go and identify these variables. So if we read our problem, at 1.20 atmospheres, that's a pressure. This is the first time pressure is being mentioned, so I'm going to call it pressure 1. And that's 1.20 atmospheres. I keep reading. A sample of gas takes, okay, here's another number, and they seem to be connected. Liters. Liters means volume. This is the first time volume is being discussed. I'm going to call it volume 1, 3.14 liters. Now, this first pressure and volume dictates what units our second pressure and volume must be at. So our P2 must be in atmospheres. Our V2 must also be in liters. So if we keep reading our problem, we see that our next pressure is given to us in torr. That means we have to convert. Okay, so remember, if we look back at that conversion factor, we had 1 atmosphere is equal to 760 torr. So if we've got 1600 torr, I'm going to set up my problem. Torr's on top, so torr needs to come on bottom. 760 goes with torr. We want atmospheres, so atmospheres goes on top. It's 1 atmosphere. So I've got 1600 divided by 760, and I'm getting 2.1 to keep those 2 sig figs, 2.1 atmospheres. Okay, so I've got a pressure 2.1 atmospheres, and we're solving for V2. Okay, so let's talk about how to work this problem. Remember, our formula was P1 times V1 equals P2 times V2. I like to just go ahead and put those numbers in. Some people like to rearrange this formula. I like to just put the numbers in. So in P1 spot, I'm going to put 1.20. In V1 spot, I'm going to put 3.14. In P2 spot, I'm going to put 2.1. And in V2 spot, I'm going to leave that V2 because that's what we're solving for. Now I'm trying to get V2 all by itself, and right now it's being multiplied with 2.1. So I've got to get it over to the other side by dividing. Okay, so now we have V2 equals, so we've got 1.2 times 3.14 divided by, we don't need any parentheses or anything, 2.1 equals, I've got 3 sig figs, 2 sig figs, 3 sig figs. 2 sig figs is going to win. And so volume 2, I'm getting 1.8. And remember, that has got to be liters. So let's look and see if we agree with this here. Our pressure increased. And so our volume should decrease. We went from 3.14 to 1.8. That's a decrease. That looks good. Let's work one more problem. Divers get the bends if they come up too fast because gas in their blood expands, forming bubbles in their blood. If a diver has 0.05 liters of gas in his blood under pressure of 250 atmospheres and then rises instantaneously to a depth where his blood has a pressure of 50 atmospheres, what will the volume of gas in his blood be? Oh my gosh, that was a lot of question. But we only need a few things. Let's go for our first number. That's 0.05 liters. Liters is a volume. So volume 1, I have got 0.05 liters. Let's keep reading our second number. That's a pressure. And they're connected of gas in his blood, and it's still part of the same sentence, 250 atmospheres. That's pressure 1, 250 atmospheres. You've got to learn those pressure units so you identify them as pressure units. Atmospheres, kilopascals, pounds per square inch, millimeters of mercury, torr. Make sure you look at that. Okay, let's keep reading. Our next number is 50 atmospheres. That's another pressure, so that's going to be our pressure 2. 50 atmospheres. What will the volume be? We're looking for volume 2. Atmospheres. Atmospheres, we're good on our units. So I'm going to put my formula again. Pressure times volume equals pressure times volume. P1, that is 0.05. V1, 250. P2, that was 50. And we're solving again for V2. Now I want V2 all by itself. Right now it's being multiplied by 50, so we need to get 50 to the other side by dividing. Okay, so let me put this in the calculator. I've got 0.05 times 250 divided by 50, and I am getting 0.25 liters. That is a dramatic increase. If you had 0.05 liters of gas in your blood, and then all of a sudden you had 1/4 of a liter of gas in your blood, that seems like you would definitely be having problems. Okay, so that's how to use Boyle's law with calculations. Make sure you understand the concept behind Boyle's law and that you know how to calculate using Boyle's law. Stay tuned for the next law, Charles. Charles is coming next. Until next time, bye y'all.